Once again, good morning, everyone, and welcome to our general mathematics class. Today, you'll discuss lesson 2.4, the last lesson for chapter 2, and it's about solving rational functions. Actually, in the past semesters, this is not all about just solving, it's about graphing rational functions. But with the most essential learning competencies, we only have the solving and we eliminate the graphing. So let's now start by reciting today's memory verse. It's found in Romans 12, verse 1. And our keyword is rational. It says, "Therefore, I urge you, brothers and sisters, by the mercies of God, to present your bodies as a living sacrifice, holy and well-pleasing to God, which is your rational act of worship." Now, in our lesson today, we'll be talking about asymptotes. Now, what is an asymptote? An asymptote is a line that draws very close to another line, but it will never cross the line. Like, for example, if this is your axis, then an asymptote will look like this one. It will go closer and closer to the main line, but it will never cross the line. Now, your MVC boosters today is about your life's asymptotes. When you get closer to achievement, dream, or even to a person, but never get a hold or touch on it, we call that an asymptotic moment. What are your life's asymptotes? You need to share one. And what lessons have you learned in your asymptotic moment? Now, give me a moment, please. So as what I've mentioned a while ago, this is the asymptote. It draws closer and closer to another line, but it will never cross the line. They say that sometimes our relationships are like asymptotes. We get closer and closer to each other, but we're not meant to be together. So share, what's your life's asymptotes? Now, at the end of today's lesson, we'll be able to do these things. First, represent a rational function to its table of values, graph, and equation. Second, we find the domain and range of a rational function. And the last is we determine the intercepts, zeros, and asymptotes of rational functions. Now let's start. Let me just skip with the venture with me. Let's go directly to our chat with the expert. Remember that a rational function is in the form of f of x equals p of x over q of x, where the numerator and the denominator are both polynomials, and our denominator should never be equal to 0, or else if it's equal to 0, then your function becomes undefined. So now, how do we find for the domain and the range of the function? Let's start first with the domain. Remember that the domain is a set of all your x values. That's the domain. While the range is the set of all y values. It's easier to locate the range if you already have your asymptotes in the next part of the lesson. But for the domain, we need to check on our denominator. Our denominator should never be equal to 0. So for example, we have 1 over x. Then you take the denominator, x is not equal to, should never be equal to 0. Or else your function becomes undefined. Now let's have some examples. we give the domain of the following rational functions. Let me start. Again, you just look at the denominator. X should never be equal to 0. So how will I write my domain? I'll say that my X can have all real numbers except 0. Or in set builder notation, we write it this way. X such that X is an element of a real number except 0. That's it. Moment, please.
21 ng guro. Lagi.
Now let's go to the next one. Ready? Just take the denominator. X minus 1 should never be equal to 0. Transfer to the other side. X should never be equal to 1. The next one. The third. X squared minus 9. That can be factored as X minus 3 times X plus 3. And that should never be equal to 0. So let's solve on the first one. We have X should never be equal to 3. That's the first. The second is X should never be equal to negative 3. So how do I state my domain? Our domain will be all real numbers except 3 and negative 3. The second one, all real numbers except 1. Now let's go to the next part. Any questions for the domain? For sure, you can just see how the domain for number 4 and 5. It's already easy. No questions? Then again, how to solve for the domain? The denominator should never be equal to 0 or else becomes undefined. And how do you state your domain? We say all real numbers except what number or what numbers. Let's go to the next part. The next part is on solving for the asymptotes. Now, there can be two asymptotes. We call it the vertical asymptote and the horizontal asymptote. Now, what is an asymptote? I told you a while ago that an asymptote is a line or a curve that the graph of a function gets close to but does not touch. For example, if your asymptote is x equals 1, then it would mean that if this is 1, this will be our asymptote. So if you have a graph, it will just move closer to the mean, to this x equals 1, but it will never cross x equals 1. Now, there are two kinds of asymptotes. We have the vertical asymptote, that's x equals a number, and the other is the horizontal asymptote, y equals a number. So in here, this is our x asymptote, our vertical asymptote, and if we have y equals 1 as our horizontal asymptote, it will look like this. So it means that the graph will never pass by these two asymptotes. Now let's start with a vertical asymptote. How do we solve like this one, the vertical asymptote and the horizontal asymptote? Now, how do we solve for the vertical asymptote? Now, the vertical asymptote is taken from the domain. So if our domain is x is not equal to 2, then our vertical asymptote will be x equals 2. The next one, if our domain is x should never be equal to -3 and 3, then our vertical asymptotes will be x equals -3 and x equals 3. But here, we need to be very careful of holes. Now, what is a hole? A hole is, just like how do we do it? A hole is a point where it's not part of the graph and it's also not an asymptote. For example, if you have a graph like this and this is your hole, so your graph might look like that one. It means that it can be a part of the graph, but because it's a possible asymptote, so it remains as a hole. Now, when can we solve, or when can a hole exist? A hole exists when you factor out your numerator and you factor out your denominator, and it's the common factor for the numerator and denominator. Example, in this one, x plus 2 is seen both in the numerator and in the denominator. So we cancel it out. So what will happen? In the denominator, if you'll see, our possible holes, our domains are x should never be equal to -2 and 3. And our possible vertical asymptotes can be x equals -2 and x equals 3. But since x plus 2, which will be transposed to x equals -2, is a common factor, then this one, the x equals -2, is no longer an asymptote, but it becomes a hole. Another example, we have f of x. Example, we have x plus 5 times x minus 6 over x plus 2 times x minus plus 5. Here, your domain based on your denominator should be x not equal to -2 and -5. But x plus 5 here is a common factor, so we cancel it out. Therefore, your vertical asymptote is only the other one, x equals -2. What happens to -5? It is called our hole, x equals -5. Now, how about the horizontal asymptote? The horizontal asymptotes can be determined by comparing the degree of your numerator and your denominator. So what will you do? First is you need to arrange from the highest exponent to the lowest exponent in your numerator and denominators. Then find the degree for each. Example, in the first one, there's no exponent, so the degree of your numerator is 0. For the denominator, that's only x, so it means we have an exponent of 1, so the degree is 1. Next, for the second one, here, numerator, that's only x, the degree is 1. Denominator, only x, the degree is 1. In the third example, we have x squared. So the degree is 2 because that's a square. In the denominator, we have only x. So the degree is 1. Now, why is it important to find the degrees? Because here's how we solve for our horizontal asymptote. If the denominator's degree is greater than the numerator, then our horizontal asymptote is automatically y equals 0. Example, the first one, the denominator's degree is 1, the numerator is 0. So this is greater. So our horizontal asymptote is automatically y equals 0. If the degrees are just the same, then our horizontal asymptote is a fraction of the leading coefficient. It means the number that goes with the highest exponent of the numerator over the denominator. Example, in the second one, the degree for the numerator and denominators are just the same. So what's our horizontal asymptote? You just have your leading coefficient. That's y equals 5/2. Don't forget y because it will help you plot in the axis. Next, but if the numerator's degree is greater than the denominator, then we say there is no horizontal asymptote, like this one. So we say there's no horizontal asymptote. But we also have an oblique or slant asymptote. Now, if the numerator's degree is greater than the denominator, the graph has no horizontal asymptote. Instead, it has an oblique, means slant, a slant asymptote. How do you find for it? We divide the numerator by the denominator, then we plot the points in our oblique asymptote. Let's go, let's have this one. Ready? Let me start with number 1. The numerator's degree is 0. The denominator's degree is 1. This one is greater, right? So our horizontal asymptote will be y equals 0. How about the second one? The same for the numerator, it's 1. Denominator, it's 1. So the leading coefficients, that's y equals 5/2. Next, the numerator is 0. The denominator is 2. It's a squared, so it's greater. So based on our rule, our horizontal asymptote is y equals 0. Next, number 4. The numerator's degree is 2. That's squared. Denominator's degree is also 2. That's squared. So our horizontal asymptote is, you see, 1/1. So 1/1, that will be y equals 1. Then the last, the numerator's degree is 2. The denominator's degree is 1. This is greater. So we say no horizontal asymptote. How about the vertical? Here, you go back to your domain. X is equal to -1. The second, 2x is equal to 8. Divide both by 2, so x equals 4. The third one, that can be x plus 2 and x minus 2. So our vertical asymptotes will be x equals -2 and x equals 2. So that's it. And you can continue till the end. Now, any questions for the asymptotes? No questions? Let's go to the next part, the zeros. Now, the zero of the function is just taking the value of the numerator. You need to solve for the variable in the numerator. Now remember, if you have a function again, let's have a very brief review. The domain is taken from the denominator. but it should be not equal to. The vertical asymptote is taken from the denominator, but an equal sign, while the zeros of the function is taken from your numerator. So again, the zero of the function should be taken from your numerator. But here, in case the numerator and denominator are both factorable, we need to factor them out, and the common function factors, we call them wholes. Let's have some examples. Ready? The first one, no variable. So we say no zeros. The second, again, the zeros is taken from the numerator. We have 5x equals 0. Divide both by 5. So our 0 is 0. X equals 0. It means it's at the point of origin. The next one, 2. There's no variable. So we say no zero. The next one, this can be factored out. That is x minus 2 times x minus 2. For the denominator, we have x plus 3 times x minus 2. So here, x minus 2 is common. So we cancel them out. It means that 2 is a whole. So what's our 0? What's remaining? Sorry. What's remaining in the numerator? There's none, right? So we say that we don't have any 0. No 0. Next, the last one. You will factor the numerator. Let us do the trial and error first. That's 2 times 1, negative 3 times 1. So negative 6 plus 1, that's negative 5. Okay. So we have 2x plus 1 times x minus 3 over x minus 2. There's nothing common, right? So the numerator will have 2 zeros. Let's start with the first one. 2x plus 1 equals 0. Transpose. 2x equals negative 1. Divide both by 2. So our first 0 is negative 1/2. How about the second one? X minus 3 is equal to 0. So x equals 3. So our zeros are negative 1/2 and 3. Any questions for the zeros? Before I'll go to the last one, the intercepts. Okay, if there are no questions, we go to the intercepts. Now, we have 2 intercepts. What do you mean by an intercept? An intercept is a point that crosses by the x and the y axis. So for example, if this point crosses by the x axis, we call it the x-intercept. If this point crosses by the y-axis, we call it the y-intercept. Now, how do we solve for the x and the y-intercept? If you'll solve for the x-intercept, you need to make your y 0. If you'll solve for the y-intercept, you need to make your x 0. But let me teach you a technique. The x-intercept is the same as the zeros of the function. while the y-intercept will be the constant terms. Example. Okay, let's remember this one, the previous one, because it's a continuation. You can take a photo of that. So as we go to the next one, we no longer need to solve, but we'll just copy. Now let's start. The first one, let's solve for the x and the y-intercepts. Oops, sorry. 1, 2, 3, 4, and 5. Again, your x-intercept will be the same as your 0. The x in the x-intercept, the x is 0. Sorry, it's xa. So a0. There's a value for x. Sorry. In the x-intercept, there's a value for x, and your y is 0. So let's start with the first one. Based on our pictures in the first one, there's no x-intercept because there's no 0. The second one, our 0 is 0. So our x-intercept will be 0, 0. The third one, based on our previous answer, there's no roots. So there's no x-intercept. In the fourth one, we only have a whole, right? So there's no x-intercept. In the last one, we have 2. We have -1/2. So -1/2, 0. And the other is, let me check again, 3. My pen, 3, 0. So these are our x-intercepts, the same as your roots. Now, how about your y-intercept? In the y-intercept, the x is 0, and there's a value for y. Now, how do we solve for the y-intercept? Just have the constant terms. It means the terms without a variable. So the first one, 1 divided by 1, that's 1, right? So 0, 1. Next, we don't have here 0 only. 0 divided by -8, that's still 0. So 0, 0. The next, I'll place 0 for the first ones. 2 divided by -4, that's -1/2. The last, 4 divided by -6, you have -2/3. And the last one, -3 divided by -2, we have 3/2. That's my technique. So again, let's have a very brief review. How to solve for the domain. The domain, your denominator should never be equal to 0. And you say all real numbers except what number? Next, for the asymptotes, the vertical is solved based on the denominator, but this time equal. Next, your range. Your range is solved based on the degree of the numerator and denominator. If the numerator's degree is less than the denominator, we have y equals 0. If they are the same, the fraction of the coefficients. If the numerator's degree is greater, then we don't have a horizontal asymptotes. For the zeros of the function, you need to equate the numerator by 0 and find It's the value for the variable. For the x-intercept, the same as your zeros. And for the y-intercept, just a fraction of the constant terms. Now, this ends today's meeting. Any questions?